Hi there, it's review of lecture 29 on singular value decomposition, or SVD. So straight away, I will first introduce you the main idea that will be introduced in this chapter. So the main idea is of factorizing A into this form, U, sigma, and V transpose. And here we're transposing A into some orthogonal, diagonal matrix and another orthogonal matrix. So notice that we need these two orthogonal matrices of U and V, which we will describe in the next part what is inside this matrix, and also we need the diagonal matrix here, the sigma. And so briefly, you might have already familiar by now with this form that A is Q, capital lambda Q transpose. And here in this case, if you remember that the Q being square and orthogonal, so we can use this property of Q inverse equal Q transpose, you remember that. And this is diagonalizing the A in case of when A is the symmetric, positive and definite. And also actually this form is actually the SVD. This is actually already the singular value decomposition for A in case of when A is symmetric and positive definite. So just to mention that we already actually ran into this SVD before, but we just don't realize it, because see here we also have these two orthogonal matrix and one diagonal matrix. So that's about my first point here what I want to mention. And now let's switch our focus into describing what is inside the U and V matrix, which will be the orthogonal vectors of U and V. Okay, let me delete some of these first. So let's define our matrix A, which is in the size of m by n, right? And then let's define our U to be at the orthogonal basis for the column space, while V here is the orthogonal basis for the row space. So if you remember that important image that we have in previous lecture about the four subspaces, let me draw something here like this. And then we say that this one is our row space, this is our row space. Okay, and this is our column space. And this one lives in Rn while this one lives in Rm. Okay. Now, what we are looking for is some kind of orthogonal basis vector here. Let's say V1 and V2. Okay. And then I'm looking for V1 and V2 such that when I multiply V1 by A, I get U1. And the same thing when I multiply V2, I get U2. And the thing is that U2 also is our orthogonal basis in the column space. So this is like illustration of U2, and this is U1 and U2. Okay. In fact, it is not only like just equal to U1, it also has some scaling factor here of sigma 1 and sigma 2, which of course can be 1 or can be any number. But the idea is that we want to first find that orthogonal vector in our row space V1 and V2, and then when we multiply A, it will be equal to some orthogonal vector in column space and scaled by some scaling vector here. And then I just want to mention that that orthogonal also implies orthonormal. Okay, so this is a really important step. So we also need to make those vectors of orthogonal into orthonormal. Why? Because later on we want to utilize this property of inverse equal to transpose, but we will see that later on. Okay, now let me just summarize so far, like how the U and V in terms of the column space and the row space that we have here. Okay, so the U and V in the 4 fundamental subspace, and I say 4, why? Because if you remember that we also have the null space here in the row space, the null space of A, if you recall that, while for the column space we have the some kind of like this. Sorry for the really terrible image, but the left null space of NA transpose, and these are all perpendicular. So if I want to summarize all of a U and V in terms of the row space and column space and all the null space, then we have first we have the from V1 to VR. This belongs to the row space, like the orthogonal vector in our row space, and where R is the rank of the matrix, right? While for U, we have U here in the column space, so U1 to UR is our lifts in the column space. So these are again the orthogonal basis vector for row space and column space. But then we also there's a possibility that our matrix being singular here, so we have some vector that lives in the null space and in the left null space, meaning that the matrix A can be not full rank to begin with. So there's a possibility of for rank +1 to VM, this is in the null space or the null space of A, while the U R until the UN, this lives in the left null space or the null space of A transpose. Okay, so after defining that, let's go back into this definition. So right now, let's put all of those here. So we have all our components. Let's say we already have a V1, which equal to some scaling vector U1 until some VR, right? Until our scaling vector R times UR. Then if we transform this into the matrix language, then what will we have? Always, because we're always interested in matrix language. If you have been following so far in the course, we always transform them into some matrix language. Then we have A, V, of course, and U times the sigma, right? Because we want to multiply the U by some coefficient here, and sigma being the diagonal matrix. So in here, A, we begin again with M by N, right? And the V here, we have, it is in the row space, so we have N components inside, and then we have the rank in the column. And for U, we have M components because it's of the column space. We have R, and for the scaling factor, of course, we have R times R. Cool. But that is not enough. So that brings us to the third point. So we have discussed the second one. So you remember I also told you there's also a case where A is not full rank, meaning that there is also case that we can include this one. So let's try to include that here. So V, let's do it here. So A, if we see inside the matrix V here, what we have is V1 until VR. But now let's add some more. So VR until VM, right? And then we also have the same thing accordingly with U1. We used to have only until UR, but now let's add until UM. Because U is in the column space, okay, it includes as well the left null space. Right, and what about the diagonal, the sigma one? So the sigma goes until R, but there's just some extra zero right there. The extra zero is from the sum of m minus r plus the n minus r. Why 0? Because again, the null space, it's scaled to 0, right? Everything that starts from here, 8 times everything here, will be scaled to 0. So that's why we kind of switch off those elements here. Let me do this in green, so just to emphasize that this thing coming from the null space. Cool. So now the dimension change. Okay. So if we include the null space components, then we will have the A. Let me do it here, because this is just such a nice comparison here. So this is with the null space. And the above one is the, I'm sorry, that's actually not getting in the screen, right? I hope it's getting into the screen. So let me put it here a little bit. So with null space, okay. And this one is without null space. So with null space we have here, but with null space now our dimension of A, V, and U and sigma change. So the A is still the same, okay, but the V becomes n times n, and the U, you guess it, becomes m times m, and the sigma becomes m times n as well. Cool. Now notice that this V right here, if we include everything, and the U, they are square matrix. And actually, I just want to mention that it's not a problem at all to include those things in our null space, because to begin with, the definition is that our null space also orthogonal to this one, remember? So our null space orthogonal to everything in V1 and V2, and as well our component in left null space are also orthogonal to everything in U here in the column space. So regarding orthogonality, there is no problem with that, okay? Just want to quickly mention that. And go back to the square things of V and U. So this is where we can implement this shortcut here of the Q inverse equal Q transpose. Let me tell you why. So let me bring this equation here. So AV now equals to U sigma. Then I can transpose, I can bring V to the other side. V inverse. Now we see that V is square. Then we can have the U sigma V transpose. Now this equation right here is what I introduced initially. You see it here is the heart of SVD. Let's put a little heart there. So that is it for the first part. I'll see you in the second part for some example. Thank you.